Hello, this is Jonathan Doolin. I am continuing my exploration of planetary core and surface temperatures by Douglas J. Cotton, published in SSRN Electronics Journal in 2013. In my last video, I finished up by looking at this diagram and noticing how 55% of the radiation from the sun, the visible light radiation, reaches the sun in this diagram, and then from the ground, actually, okay, it looks like 25% here is represented by this column. 25% of the sun's energy comes out, which is broken up into, sorry, this would be 21% of the sun's energy, and 21% is broken down into 15% that is reabsorbed by the atmosphere, and 6% that goes all the way from the ground to the earth. So that factor of 21, 6 divided by 21 is actually about 28.6%. 28.6% of the infrared from the ground actually makes it directly out of the atmosphere. Anyway, these numbers that he gives here are not exactly well represented by the diagram. Okay, he then goes on to say calculations using standard physics. I'll put it here. Now, calculations using standard physics show that the direct solar radiation, such as that received by Earth's surface, could not have raised the mean surface temperature by the observed amount. Why would he say that? Okay, so Douglas Cotton's statement is that calculations using standard physics show that direct solar radiation could not have raised the mean surface temperature by the observed amount. A statement consistent with an understanding of the greenhouse model would be that Stefan Boltzmann's law of radiation is not by itself sufficient to explain the Earth's surface temperature. So, but if you take Stefan Boltzmann's law applied to the tropospheric surface and the law of thermal insulation applied for the height of the troposphere, these together are sufficient to explain the surface temperature. He then goes on to say this is even more obvious on the planet Venus because their surface there receives barely 10% of the solar radiation that Earth's surface receives, and yet it's been measured at over 450 degrees Celsius. Okay, what he just said is this. He's saying that the surface of Venus only receives 10% of the solar radiation. Most of it is blocked, 90% of it is blocked by the gas of the atmosphere. So let's look at his principle then, and we'll separate these into Douglas Cotton's principle for a good heating gas, and we'll compare it to my Jonathan Doolin's principle for a good heating gas. And his idea of what makes a good heating gas is that what makes an effective heating gas is how much energy the gas is able to transmit transparently to the ground. So his principle in mathematical terms is basically that the transparency of the gas, if it's 100% transparent, then that would make it 100% effective in heating the ground. My basic premise is that you can do better than that. And what makes for an effective heating gas is its ability to maintain a temperature gradient between the bottom and the top of the troposphere. I'm going to give a description now, and I'm going to kind of break with my cardinal rule of making the input energy equal to the output energy. That's the case for equilibrium. But let me think about a system where we've got a 5800 Kelvin source over here, which is the sun, and we're going to say that the energy in is 100% and the energy out is 100%. What happens to the temperature of this object? Nothing. The temperature of this object does not increase or decrease as long as the input and output balance. So this is the situation that you would probably get on an asteroid or any object out in the solar system that doesn't have an atmosphere at all, or any object that would have a pure nitrogen or oxygen spectrum would be like that. Now let's describe the state of Venus. Or at least what it would be like if you were on Venus before it reached its equilibrium temperature. So we're going to have we're just going to have 10%. 10% of the light gets in through that atmosphere. 90% of it just reflects off. But then it's absorbed, and how much of it comes out? Only 1%. Well, as long as you're in that condition where you have more in than you have coming out, like if this part comes through transparently and this part leaves transparently, then you've got this constant input of like 9% of your energy incident is coming in to heat this area. So 9% plus 9%. Eventually, the maximum theoretical temperature that this could be is 5800 Kelvin. So in principle, if you have any part of this 5800 Kelvin energy coming in, the equilibrium temperature is like first or zeroth law of thermodynamics, that two objects in thermal equilibrium are the same temperature. So that is what we're headed for. Theoretically speaking, that is the maximum temperature that this body could be. Same thing with Earth. If we basically said 100, if we ended up with somehow 100% in and 0% out, and we stayed in that condition for a long while, eventually the Earth would reach 5800 Kelvin, and that would be the equilibrium temperature with the sun. So what makes for an effective heating gas is its ability to maintain a temperature gradient between the bottom and top of the troposphere, or to put it another way, it is the ratio of input transparency to output transparency. So Douglas Cotton continues, so there appears to be something very wrong with the assumption that the surface of the planet is 33 degrees warmer purely because the atmosphere slows the rate of cooling. Okay, so he's saying there appears to be something very wrong in the assumption that the surface of the planet is 33 degrees warmer purely because the atmosphere slows the rate of cooling. Let me put it the way I would say it. If we have a system in a state of non-equilibrium, so this is a state where temperature, say the temperature with the sun is not, well, wow, 5800 Kelvin, that's our equilibrium temperature with the sun. Yikes. But we have the output transparency is less than the input transparency. Basically the light going out of the system is in the infrared. So the output transparency is low, and compare it to the input transparency. That's the That's the transparency of the atmosphere in visible light, which is fairly high, the high transparency. The surface will gain heat through the input at a faster rate than it loses heat through the output. Now, the input medium is the air, and the output medium is the air. So it's the same medium, but the form of the heat is visible light on the input and infrared on the output. So on the input, the energy has high transparency, and the output, the energy has low transparency. So the question is, if the sun cannot raise the surface to a higher temperature first, we have to ask, cooling from what? So the temperature, the equilibrium temperature of the sun, if the Earth and Sun reached an equilibrium temperature, that temperature would be around 5,700, 5,800 Kelvin. 5,778 Kelvin. So that is our, if we had a perfect greenhouse effect, if the Earth let in all the energy from the sun and it let out nothing, this is the temperature we'd be looking at, 5778 Kelvin. Or if it just, and it wouldn't have to be letting in 100% and outputting nothing. It could be allowing in any tiny fraction of the sun and letting out nothing. The key is that the ratio, as long as the ratio is infinite, then of input to output, as long as the ratio of input to output is infinite, if the denominator is 0, then we could have a greenhouse effect where the object being what do you call it, insulated, would reach 5778 Kelvin. As an example, the inner core of Earth is considered to be about 6,150 Kelvin, so it's actually a little bit hotter than the surface of the sun, but it's a situation where you have almost zero energy coming in from the sun and almost zero energy coming out from the sun. But the temperature actually ends up being fairly close to the temperature of the sun. But this temperature is not probably predominantly the result of the greenhouse effect. Although it probably doesn't hurt that the greenhouse effect is there. Okay, Douglas says, as will be explained in later sections, it is the effect of gravity that does the bulk of the warming by spreading energy in the atmosphere and creating a thermal gradient. That will surprise me, but I guess we'll find that out when we get to it. All this cooling of the surface is merely a marginal process which holds back the small amount of energy which is absorbed when the sun shines and then transferred back to the atmosphere. I'm kind of at a loss right now because like just now he asked the question, cooling from what? I'm not sure, did he mean that to be rhetorical? Because the clear answer is cooling from the equilibrium temperature, cooling from the equilibrium temperature of 5,800 Kelvin degrees. And the sun could potentially raise a surface to that temperature if it demonstrated a perfect greenhouse effect. And then he says all this cooling, but I'm not sure what he means by all this cooling. I'm not sure what he means by a marginal process. I'm not sure what he means by holding back the small amount of extra energy which is absorbed when So meanwhile, an underlying stable base thermal profile in the atmosphere ensures that air near the surface cannot cool or warm too much, and nor can the surface. So this is his description of an underlying stable base thermal profile in the atmosphere. I don't know what that means. An underlying stable base thermal profile. So this, let's just guess that this entire paragraph refers to something that he's going to explain later. And we'll go on to section 3. The Venus dilemma. So a greenhouse effect is even less believable when we consider the planet Venus, or indeed other planets with dense atmospheres, namely Jupiter, Saturn, Uranus, and Neptune. Okay, and he's just using this, he's not calculating things in terms of a ratio. Douglas is not calculating things in a ratio. He calculated that 2.5% of incident solar radiation gets through to the surface. Okay, so 2.5% of incoming radiation compared to what amount of outgoing radiation? That's the key question. What is the and the answer to that question is going to be about 100%. It's going to be 2.5%. It's going to be about 2.5% in to 2.5% out. Or no, it's not going to be 2.5% in to 2.5% out. It's going to be that the energy coming in, this is the 2.5% of the incident visible radiation coming in, compared to the energy of the outgoing radiation, is going to be about 100%, as long as the state of the atmosphere is in equilibrium. However, if the state of the atmosphere is not in equilibrium, then if the state is not in equilibrium, you will have an amount out that is less than the amount coming in. And if there's a state of non-equilibrium like this, then the planet will heat. So all of this is due to his failure to compare the he's not comparing the input to output. He's just talking about the input and saying, ooh, that's pretty low. But it's low compared to what is the question. He says it is obvious that the atmosphere is being heated primarily by incident solar radiation rather than a very small amount of radiation returned by the surface from that 2.5%, which made it through the dense atmosphere. And I mean, so here, I mean, honestly, he's not exactly wrong, because if the system is in equilibrium, then if the system is in equilibrium, then yeah, the heating. So this is what the system looks like on Venus. You got the incoming light rays striking that surface of 300 degrees Celsius, the outer surface of the atmosphere. It sounds like he's saying about 85% of that, 85% of those rays are basically bounced off of that surface, and 15% of those rays make it in, and down there they're absorbed by that planet or by the nearby gases. Somehow the 15% of that light gets down to the bottom, and then that heats up this area to 700 degrees Celsius, and we don't really, the system's in equilibrium, we really don't even have to think about the returning rays at that point. We just say, okay, this thing emits an infrared spectrum at 700 degrees, and eventually all of that light that is at 700, well actually this emits a spectrum at 700 degrees Celsius, but it climbs up through the atmosphere until all that is free to leave the surface is actually an infrared spectrum at 300 degrees Celsius. So there's a significant drop in the temperature before that infrared light is actually output into the universe, into space. And it goes on to say, one might indeed assume that the top of the Venus atmosphere would be hotter than the base, as surely more incident radiation would be absorbed up there. But that would, I don't know why he would say that's something anyone might assume. That is utterly incompatible with the greenhouse effect, the theory of the greenhouse gas effect. It is the bottom surface of the atmosphere that is at the bottom of the blanket, and the top surface of the atmosphere is the top of the blanket, so it is the bottom surface that is hotter. The reality is that the base of the atmosphere is more than 400 degrees above the mean radiating temperature for the whole planet plus atmosphere system. So it is hotter at the base and much colder at the top. So that is in agreement with the greenhouse effect idea. Let's go back to when the planet first formed and imagine that the surface temperature to be about the radiating temperature of the planet, which would be a bit warmer than the Earth's. So he's imagining that instead of this being 700 degrees Celsius, or 700 degrees Kelvin, let's call it 700 Kelvin and 300 Kelvin over here. He's imagining that the surface there is 300 Kelvin, and let's see where he goes from there. So perhaps you are thinking that heat would somehow build up over a million years to achieve the temperatures we now observe. Well, would they? Okay, we've got this 5800 Kelvin source over here, 5800 Kelvin. And we've got heat coming in at 5800 Kelvin. So this surface, if it's absorbing that light from there, it would potentially be lifted up to a heat of towards 5800 Kelvin. And so as it was lifted up towards 5800 Kelvin, the atmosphere would become more, well, it would not, actually it wouldn't go towards 5800 Kelvin unless you assumed that there was some greenhouse gas around it. What would happen is basically you'd look at that 5800 Kelvin and you'd apply, let's see, where does it go? Power times area equals sigma ET to the fourth. And we'll say power in times area equals sigma ET to the, and this is going to be our T sun to the fourth. And that area in, I'll go ahead and write that down, area in is equal to pi r squared, where r is the radius of the planet. And we say P out times the area out equals 4 pi r squared, which is 4a in. So say 4p out equals 4p out a in equals sigma e t t surface to the fourth. This is called Stefan Boltzmann's law. I've written Stefan Boltzmann's law twice here. And then I'm going to solve for the T sun and the T surf, which actually I'm just going to divide out area in. I'm going to divide out, this sigma doesn't really need to be there. The emissivity, I'm going to just say, for the sake of argument, that the emissivity is 1 for both the input and the output frequencies of light. And I'm also going to claim that power in is equal to power out. So this is not, I'm not actually calculating the, I'm not actually trying now to deal with the actual rising of the temperature. I'm just trying to figure out what that temperature will be when we get there. So what we basically have is, I shouldn't have crossed out P out equals P in. What I should have done is write P out equals P in. P out, which is T sun, this is going to be T sun to the fourth, and this is going to be T surface to the fourth over 4. And what I find is I definitely did not do that right. Alright, I decided to go into Desmos and work out the problem with the help of technology, because doing it by hand is complicated. First of all, sigma, which is called Stefan Boltzmann's constant, is 5.67 times 10 to the negative 8th, and it's in something like watts per meter squared per, I forget the exact units, but the radius, I guess I don't need this for my calculation. This is the Earth-Sun radius. Venus-Sun radius is, Venus is 108.61 billion meters from the Sun. Then the radius of Venus is 6.05 million meters. And the temperature, or the radius of the Sun is 696 million meters. Temperature of the Sun is 5778 Kelvin. And then I'm going to apply, this is Stefan Boltzmann's law, that the power of the Sun is equal to sigma times the area of the Sun, which is 4 pi times its radius, times its temperature to the 4th power. And I did not include E in here, the emissivity, but I'm just assuming it is 1. The intensity that reaches Venus, then, is the power of the Sun divided by its cross-sectional area. Well, no, I'm sorry. The intensity that reaches Venus is equal to the power of the Sun divided by the surface area of a sphere that goes all the way out to Venus. And then the cross-section of Venus is equal to pi times the radius of Venus. And the surface area of Venus is 4 times that cross-sectional area. And so we're going to figure out what the power coming into Venus is, which is the intensity of the sunlight at Venus, which was 2,598 watts, times the cross-sectional of Venus, which was this number here. And it comes out to be, no, this number here was the cross-section. And it comes out to be this number. And finally, we're going to take that number to find the temperature. We're going to take the 1/4 power of the power into Venus divided by Stefan Boltzmann's constant divided by the area of the surface of Venus. And it comes out to be 327 Kelvin. So he says, perhaps you are thinking the heat would somehow build up over a million years to achieve the temperatures we now observe. I got 327 Kelvin from that calculation. But and he says, well, unfortunately, but of course, that temperature does not have the greenhouse effect factored in. What's he say? Unfortunately, the second law of thermodynamics prohibits that. When radiation leaves the surface, even if all of it returns back radiation, the net result cannot cause the temperature to rise. Okay, let's talk about what would happen if we had all of the radiation turned back. Okay, earlier I calculated the power into Venus, which is equal to the incident intensity of 2,597.7 watts per square meter times the cross-sectional area of Venus, which was 1.15 times 10 to the 14th square meters. And we calculated that the input power into Venus was about 2.99 times 10 to the 17th watts. This is how many watts are coming in from the sun. And he says even if all of it returns back as back radiation. Okay, so this is all of it. So 100% of the incoming radiation returns as back radiation. All right, so what's that mean? We've got in 3 times 10 to the 17th watts, out 0 watts. Okay, what's going to happen? What's going to happen if you got 10 to the 17th, 3 times 10 to the 17th watts coming into the system? That's joules per second. And we have 0 watts going out. Is that system going to heat? You damn well bet it's going to heat. And I'll tell you, if we had a system that we could do that with, man, that would be like the most amazing solar power system that the world ever had. If it could take in 100% of the energy and store it, boy, that would be an efficient heater at least. If not, if you couldn't get any other power out of it, it would be a very efficient heater. But such as it is, we're not going to have input of 3. What is that? It's 300 petawatts of energy. 300 times 10 to the 7. 300 times 10 to the 15th watts. So if you could have that come into the system and none of it leave, boy, you would get a lot of heat out of that. Your system would be going haywire with heat. And if you could keep that up for a long time, eventually you would end up reaching a thermal equilibrium with the sun, which is about 5,800 Kelvin. So he goes in to say when radiation leaves the surface, even if the net result cannot cause the temperature to rise. That's silly. Of course it can cause if you allow heat into a system and you don't allow heat out of the system, it's definitely the temperature is going to rise. It says, yes, it will slow the rate of cooling, but it will never raise the temperature with any additional heat transfer to the surface. Well, that much, I mean, that's kind of a true argument. I mean, there wasn't any, we took that 300 petawatts from the sun. We didn't add any additional, by not letting that heat out, we didn't add any additional heat, but we just didn't let it out. So right, energy cannot be created in this process, but you can prevent it from escaping. If you prevent it from escaping from your system, it's gonna continue to keep the temperatures rising. Will the sun raise the temperature more the next day? Well, probably. If you're letting in 300 petawatts of energy. Actual measurements by Russian probes dropped on the Venus surface led to calculations that the mean radiation received at the surface on the illuminated side is on the order of 10 to 20 watts per meter squared. Because so much is reflected and absorbed by the thick atmosphere, so it is obvious that direct solar radiation could never account for an extra 400 degrees Celsius or more, and no runaway greenhouse effect could amplify energy 1,000-fold. What he's saying there, his conclusion does not follow from the premises. So this calculation shows that the intensity predicted at Venus surface is 2,597, 200,000, or 2598 watts. And he says the actual intensity at the surface, measured by the Russian probes, was 10 to 20 watts per square meter. But that's not that's not really relevant to the question. Anyway, the temperature at the temperature of the surface of the atmosphere, the surface of the troposphere, though, is probably somewhere close to this 327 Kelvin. And probably also the atmosphere, the upper part of the atmosphere, emits a light of emits a light in the range of 2,600 watts per square meter. That's kind of the nature of insulation. If I've got a whole bunch of blankets on top of me, and sunlight is coming down, and it's warmer down here and dark down here. It's going to be warm and dark down here, and up here is going to be cold and light. So that's just the nature of the green of insulation, how insulation works. So these arguments that are saying that they're anti greenhouse effect are but basically just they're just descriptions of what the greenhouse effect would predict. That you got warm dark area down here and a cold light area up here.